Welcome to the sleepy atom, where bedtime meets the vast silence of the cosmos. Tonight, let's wander into one of the strangest riddles of existence: why time itself does not behave the same everywhere. You might think a second is a second ticking evenly across the universe. Yet once you step beyond our little blue planet, you discover that seconds can stretch, bend, and even twist into something unrecognizable. The closer you look, the more time begins to feel alive, like a river that rushes in one place and slows into a gentle pool in another. Imagine holding a clock in your hand. Here on Earth, it ticks with comforting regularity. But if you carry that clock into space, place it near a massive star, or send it racing close to the speed of light, the tick no longer matches what's happening back home. Time itself has changed, and so tonight, with a calm voice and a patient mind, we'll drift through the mysteries of time's strange behavior in space, slowly peeling back the layers of a truth that is both unsettling and wondrous. Settle in. The journey begins with a single clock here on Earth. A clock ticking on Earth. Picture yourself staring at a small clock resting on a desk, the hands moving in their familiar rhythm, each second sweeping past with quiet authority. On Earth, we trust these ticks. They guide our meals, our work, our sleep. But beneath that trust lies an assumption that this rhythm holds true everywhere. The strange truth is that this little clock, so ordinary, is only telling our version of time. And when compared with other clocks far from Earth, disagreements begin to appear. Think of how unsettling that is. Two clocks built the same way, starting together at the same moment, but later refusing to agree. On Earth it feels impossible because our daily lives are too small to catch these distortions, yet the cosmos isn't bound by our sense of order. It stretches and bends time depending on where you stand and how you move. This means your humble desk clock is more fragile than you ever thought. Children sometimes ask, if time is everywhere, why can't we hold it? And adults smile, thinking it's only a childish question. But when you discover that time itself shifts under the universe's weight, the question suddenly feels wiser. What exactly are we holding when we measure a second? Even scientists were once convinced that time was absolute, a steady drumbeat across existence. This belief carried through centuries of thought, almost like a law of nature too sacred to doubt. And yet this law began to crack when the universe whispered something different. That whisper grew louder with strange experiments, as if time itself was daring us to question the very ground beneath our feet. Tonight, our story begins with that small ticking clock on Earth. And by the time we follow it beyond the atmosphere, we will see how fragile that ticking really is. But first, we must meet the man who broke our trust in time. The strange idea that time isn't fixed. Imagine the courage it takes to look at something everyone accepts as truth and to say, what if it's wrong? For centuries, time was assumed to be fixed, the same everywhere, flowing like a background stage upon which the universe performed. Then came a young patent clerk named Albert Einstein. He whispered a different idea, that time was not a stage, but a player itself, bending and changing depending on speed and gravity. At first, people laughed. How could a second be different in one place than another? Our minds cling to certainty. It's uncomfortable to think that something as simple as now might not exist the same for you and for me. But Einstein's equations were stubborn. They revealed that light always traveled at the same speed, no matter how fast you moved. To make that work, time itself had to bend. Time was not fixed, it was elastic. This discovery rippled through the world like a stone thrown into still water. Physicists wrestled with it, but the math kept proving true. And slowly, experiments began to support what had once sounded like madness. Time was not the universal drumbeat we thought it was. It was personal, relative, and alive. Think of what that means for relationships, for memory, for the way you and I share a moment. If now is not universal, then your experience of reality might not match mine perfectly. The very fabric of togetherness becomes strange. Einstein's idea didn't just bend time, it bent our understanding of reality itself, and nothing would ever feel quite as stable again. The strange idea that time isn't fixed opened a door that humanity had never walked through before. And once it was open, the universe began revealing secrets one after another, starting with how motion itself bends the seconds we live in. Einstein's shocking discovery about time. Think of standing on a train platform, watching a train rush past at incredible speed. The passengers inside glance out at you and you glance in at them. Einstein realized that what you see, the rhythm of their clocks, the beating of their hearts, is not the same as what they experience themselves. For them, time moves normally, but for you, it moves differently. This was not philosophy, it was the direct consequence of how light behaves. The shocking part is this: both you and the passengers are right. Neither perspective is wrong. Each is living inside their own time. The universe doesn't choose one truth over another. It allows both to exist. This was Einstein's radical discovery. Time is not universal. It depends on where you stand and how you move. And once you accept that, the world begins to look very different. Imagine then the ripple effect on everything we build, our technology, our journeys, even our understanding of aging itself must face this revelation. If you could move close to the speed of light, your seconds would stretch. You would age slower than those left behind. The shocking discovery was not only about clocks, it was about life itself. It's hard not to feel a shiver when you realize that the faster you move, the slower you live. Science here feels less like cold numbers and more like poetry written by the universe. We are not fixed beings in a fixed river of time. We are travelers, each carrying our own current of seconds. Einstein's shocking discovery tore away the illusion of a shared, steady world, and it left us with a question that feels almost impossible to answer. If everyone's time is different, then what is reality? The only way to explore this puzzle was to put theory into motion, how motion bends the flow of seconds. Imagine lacing up your shoes and beginning to run. Your breath quickens, your heartbeat races, yet the world around you feels steady. But in the hidden realm of physics, even this small movement begins to stretch time ever so slightly. The faster you move, the more those seconds bend. At walking pace, it is too small to notice. But at cosmic speeds, the effect becomes enormous. Motion itself bends time like a craftsman bending metal. This bending isn't metaphorical, it's measurable. Scientists realize that motion and time are inseparably linked, like dance partners who cannot let go. Push motion to extremes, like traveling near the speed of light. And time refuses to keep up with the rest of the universe. Seconds stretch, minutes linger. Your clock betrays you by slowing down compared to the one left at rest. Now picture a spacecraft slicing through the void, its crew moving faster than any human on Earth. Their laughter, their meals, their memories unfold at what feels like a normal pace. But back on Earth, the same amount of time may have passed very differently. The clocks no longer agree. This is not imagination. It is how the cosmos insists things must be. The bending of seconds is like the universe's quiet reminder that reality is far stranger than appearances. Each time you accelerate, you negotiate with time itself, bending it a little more. And while your senses don't catch it at everyday speeds, the deeper truth is always there, waiting in silence. Motion bends time, and this bending can even separate twins born on the same day. That paradox would become one of the most haunting thought experiments in science. Two lives, split by motion, reuniting with different ages. And it is here the story of time takes a turn into the realm of the strange. The faster you move, the slower you age. Here is the paradox that unsettles even the most practical minds. If one twin stays on Earth while the other boards a spaceship traveling near light speed, something remarkable happens. When they meet again, one is older than the other. They were born seconds apart, but motion itself has split their fates. The faster you move, the slower you age. This is not fantasy. It has been confirmed again and again with experiments. Time itself bends to the pace of your journey. Think about what that means in human terms. Birthdays missed, memories unfolding at different speeds, lives stretched apart by nothing more than velocity. The bond between twins, once inseparable, now becomes proof that reality is not as even as we thought. This is where science meets something almost emotional. Motion does not just change distance, it changes life itself. And yet the twin paradox is not a tragedy. It is a gift of insight. It shows us that time is flexible, alive, responsive. The universe is not a rigid machine, but something softer, stranger, more mysterious. And deep down, it invites us to wonder whether we are all living inside different rhythms even now. When you hear that the faster you move, the slower you age, it is hard not to daydream. Could this be a path toward longer life? Toward glimpsing a future others cannot see? Or is it simply a reminder of how fragile our human sense of time really is? Questions like these linger not as puzzles to be solved, but as whispers that keep us awake at night. The faster you move, the slower you age. Oh, it is a truth both humbling and wondrous. And as we open more of this journey, we'll see that experiments with real airplanes, satellites, and astronauts have already proven this dreamlike idea is reality. The twin paradox that made scientists doubt their eyes. Imagine two identical twins. One stays on Earth, the other boards a spaceship traveling near the speed of light. They wave goodbye, still the same age, still sharing the same heartbeat of life. But when they meet again, something unthinkable has happened. The traveler is younger, not by minutes, but by years. This is the twin paradox, a thought experiment so haunting that even hardened scientists paused and whispered, could this be real? The paradox isn't fantasy. It comes directly from Einstein's equations. Motion bends time. And at near light speeds, the bending becomes extreme. The earthbound twin's life unfolds with its usual rhythm, birthdays, laughter, grey hair. But the travelling twins' clock ticks slower, stretching their youth. Time is not fair, it is not shared, it is personal. This is why scientists doubted their eyes, for it sounded less like physics and more like magic. What makes the twin paradox so gripping is its human face. Two people born together, destined to age apart, not because of choice, but because of motion itself. It unsettles us because it touches memory, family, and love. It reminds us that the universe doesn't always bend to our stories. Sometimes it bends our stories to itself. And yet the paradox is not just a curiosity. It became a test, a challenge. If this strange bending of time was real, could we catch it in the act? Could we take clocks, send them on journeys, and compare their ticks? Scientists, with trembling excitement, decided to try. The twin paradox would soon leave the chalkboards and enter the skies. Airplanes carrying atomic clocks would put Einstein to the test, and the results would leave no doubt. When airplanes tested time with atomic clocks, in the 1970s, a group of scientists did something almost childlike in its simplicity. They took atomic clocks, the most precise timekeepers humanity had ever built, and put them on airplanes. These planes circled the globe eastward and westward, while identical clocks remained safe on the ground. When the planes returned, the scientists compared the clocks, and the numbers didn't agree. It was not a malfunction. The moving clocks ticked differently than the ones at rest. Einstein had been right. The universe itself had shifted their rhythm. Time bent under motion, just as predicted. The twin paradox was no longer just a strange tale in physics textbooks. It had become a fact proven by ticking machines in the sky. This was not a small difference. The shift was measurable, undeniable, and haunting. Imagine holding two identical watches, setting them at the same second, then discovering later that they no longer match. Not because of error, but because the universe itself insisted they shouldn't. It was as if time was reminding us, I am not what you think I am. For the scientists, this experiment felt like crossing a line. They weren't just proving equations, they were touching the fabric of reality itself. Ordinary passengers on those flights had aged imperceptibly differently from those on the ground. The effect was tiny but real. Time had been bent by nothing more than an airplane's journey. From that moment on, science could no longer pretend time was absolute. And soon, satellites high above Earth would reveal even greater distortions woven into the very systems we use in every single day. Satellites above us prove time is not equal. Every time you check a map on your phone, you are relying on clocks floating thousands of miles above Earth. These GPS satellites orbit the planet, sending signals timed with exquisite precision. But here's the twist, these clocks do not match ours. In orbit, time ticks differently, and if we didn't correct for it, your GPS would be useless within hours. Why does this happen? Because satellites are both moving quickly and sitting in weaker gravity than we are on Earth's surface. Both effects stretch time. Their atomic clocks tick faster than ours. Without correction, your phone would place you miles away from where you actually stand. Every map, every location, every direction you trust depends on acknowledging that time is not equal everywhere. It's humbling to realize a system we treat as mundane, a navigation app, is quietly whispering Einstein's truth into your hand every day. The technology only works because engineers accept that time bends, and not by theory but by fact. Every second, satellites prove to us that the universe's rules are stranger than human common sense. Think about how wild that is. Billions of people rely on GPS daily without realizing they are depending on relativity, on time dilation. A driver heading to work, a pilot navigating the skies, a ship crossing the ocean, all moving safely because scientists learned that time itself cannot be trusted to stay the same. It's not just satellites. Gravity itself bends time in ways we can feel if only we knew how to listen. And this bending becomes clearest when we compare the heights of mountains and the depths of the sea. GPS works because time runs differently in orbit. Your phone beeps, it shows you where you are with uncanny precision. You don't think twice. But behind that glowing dot is a miracle of physics. GPS works because time runs differently in orbit, and scientists have learned to correct the difference. Without those corrections, the system would drift. Within a single day, errors would reach kilometers. By the end of a week, your phone might place you in an entirely different city. What's extraordinary is how subtle yet powerful the effect is. The satellite's clocks tick about 38 microseconds faster per day than clocks on Earth. That sounds tiny, but when multiplied by the speed of light, the distance signals must travel, the error becomes massive. Space travel and communication would collapse without Einstein's corrections woven into the design. It's strange to think that the universe itself forces us to honor relativity in such practical ways. We didn't just discover this for curiosity, but we depend on it to move through our world. A delivery driver, a hiker in the woods, a farmer with GPS-guided tractors. all living proofs that time is not absolute and that ignoring it leads to chaos. In a way, GPS is a quiet teacher. It shows us that the bending of time isn't only about distant galaxies or theoretical physics. It's part of our daily lives. Each direction you follow, each map you trust, is secretly reminding you. The universe is flexible and time does not play fair. But there is an even deeper force that bends time, far more powerful than speed or orbit. A force we feel every day, yet hardly ever connect to the flow of seconds. Gravity. Gravity has the power to stretch time. Stand on a mountain peak and look down at the valley below. The clocks up here tick ever so slightly faster than the clocks down there. Why? Because gravity stretches time. The stronger the pull of gravity, the slower time flows. This is one of the strangest truths in science. The weight of the universe itself presses against the seconds you live in. Think about what that means. Every heartbeat, every breath, every moment of your life is subtly influenced by where you stand. On Earth, the effect is small, almost invisible. But near massive objects like stars or black holes, the stretching becomes dramatic. Time doesn't just bend, it warps, slowing to a crawl under the grip of gravity's hand. This is not imagination. It has been measured with astonishing precision. Scientists have placed atomic clocks on mountaintops and compared them with clocks at sea level, and sure enough, the mountaintop clocks tick faster. Two people, separated only by height, are already aging differently. The difference is tiny, but real. Gravity is sculpting the flow of their lives. The poetry of this truth is hard to ignore. Mountains, valleys, oceans, they are not just landscapes. They are sculptors of time. Earth itself is a machine that bends seconds differently depending on where you stand. And when you take this truth beyond Earth, into the vast gravity wells of the cosmos, the effects become breathtaking. Standing on a mountain versus standing by the sea. Close your eyes and imagine standing on the top of a great mountain, where the air is thin and the world looks small beneath you. Now imagine stepping down all the way to the sea, where the horizon stretches endlessly. The difference feels like geography, but physics tells us it is more. Time itself ticks differently in these two places. On the mountaintop, where gravity's pull is weaker, the clock runs faster. By the sea, under the weight of Earth's gravity, it slows. It's a strange thought. You and a friend could carry identical watches, then meet later to find they disagree. The difference would be tiny, so small you wouldn't notice in daily life. But in the quiet precision of science, it's there. Standing high or standing low, the Earth is quietly bending your seconds. When scientists first measured this, it felt almost unsettling. How could something so invisible, so constant, betray us like this? Yet it also felt beautiful. Mountains and oceans were no longer just landscapes. They were sculptors of time. You weren't simply walking uphill. You were stepping into a slightly different rhythm of existence. Imagine then what it means for astronauts orbiting above us. They are not only higher in space, but racing quickly around Earth. Their seconds bend differently than ours in both ways, by gravity and by speed. The mountain and the sea suddenly look like the smallest hints of a much larger truth. Standing on a mountain versus standing by the sea, it's not just about the view, it's about realizing the universe is never giving everyone the same clock. And the deeper you go into gravity, the more dramatic this difference becomes. Your watch runs faster in the sky. Hold out your wristwatch. Imagine lifting it into the sky, mile by mile, until it rests at the edge of Earth's atmosphere. If you could compare it to the one still strapped on your wrist below, you'd see something remarkable. The higher watch runs faster, not by much, but enough to remind us that gravity stretches seconds like elastic bands, and this isn't science fiction. It has been proven with atomic clocks carried on airplanes, rockets, and satellites. The further you move from Earth's pull, the freer time flows. It's as though gravity clutches at every second, holding it back, and the higher you go, the looser that grip becomes. Your watch, in the sky, escapes the hand of Earth just a little more. This truth has practical meaning. The engineers who built GPS satellites had to design them knowing their onboard clocks would tick faster in orbit. Without adjustments, our technology would collapse within days. Every direction you follow in your car, every search for a restaurant on your phone, only works because we've accepted that your watch runs slower than the one above you. Think about that for a moment. The universe forces us to live with multiple versions of time. The seconds on your wrist, the seconds in the sky, the seconds in orbit, all slightly different, yet all real. There is no single truth. There are only perspectives, and each one is valid. And if a simple watch changes speed in the sky, what happens near places where gravity grows unimaginably strong? That's when seconds don't just stretch. They begin to disappear into eternity. Black holes as the greatest time distorters. Now we step closer to one of the most mysterious creatures in the universe, the black hole. Imagine a star so heavy, so dense, that nothing, not even light, can escape its pull. At the edge of this abyss, time itself begins to twist in ways that defy comprehension. For those who fall in, seconds stretch into something unrecognizable. For those watching from afar, the falling traveler seems to freeze in place forever. A black hole doesn't just warp space, it warps time. The closer you approach its event horizon, that invisible boundary, the slower your clock ticks compared to the rest of the universe. To you, everything feels normal, but to the outside observer, you're moving slower and slower, as if being stretched across eternity. It's as though time itself cannot escape. This truth is not fantasy. Astronomers have detected how light, climbing away from black holes, stretches and reddens, slowed by gravity's iron grip. Black holes aren't only swallowing matter, they are swallowing time. The universe hides its most extreme distortions inside these cosmic abysses, and the paradox is haunting. A traveler falling into a black hole might experience minutes before vanishing, while the outside universe could age billions of years. One life stretched into unimaginable contrast, simply by gravity's power. The black hole becomes not just a monster in space, but a master of time itself. To imagine black holes is to feel small, yet strangely it also teaches us that the rules of time are not fixed. If it can be bent, stretched, and nearly stopped, then time is not the ruler of the universe, it is the ruled. Near the edge, seconds turn into eternities. Picture yourself drifting close to a black hole's event horizon. Your ship hovers, trembling, as the pull of gravity grows unbearable. To you, inside the ship, your heart beats steadily, your clock ticks normally, but for someone watching from far away, your movements slow, your seconds stretch, until you seem frozen at the edge, trapped in a moment that never ends. This is one of the strangest consequences of relativity. At the edge of extreme gravity, time doesn't simply slow, but it begins to smear across eternity. To the outside universe, you will never truly fall in. You will remain forever suspended at the brink. But from your perspective, you plunge across the horizon in an instant. Two truths, both real, both incompatible. It's as though the universe itself cannot agree on your fate. Are you frozen or have you fallen? The answer depends on where you stand, and that's the lesson black holes whisper. Time is not a universal agreement, it's a negotiation shaped by perspective and distance. What makes this idea so haunting is its echo in our own lives. Sometimes a single moment feels eternal, while years can vanish in a blink. The physics of black holes mirrors the emotions we already know, Johannes. The time is slippery, untrustworthy, and endlessly strange. Near the edge, seconds turn into eternities. And it leaves us wondering if time itself might be just an illusion, something our minds cling to in a universe that refuses to be simple. Falling into a black hole means leaving Earth's time. Imagine taking that final step, falling past the event horizon of a black hole. In that moment, you are not only leaving Earth, not only leaving the stars you once knew, you are leaving time as anyone else can measure it. To the outside world, you are gone. To you, the journey continues. The connection between your seconds and theirs is severed forever. This is perhaps the most terrifying and beautiful truth of black holes. They don't just pull matter, they divide realities. You carry your own private clock, forever separated from the universe you came from. For those left behind, your image lingers, frozen at the horizon. But you have already crossed into a realm where Earth's time has no meaning. What does that feel like? No one can know. Perhaps time continues inside, but in a way we cannot imagine. Perhaps it ends altogether. For the laws we know break down in the heart of such gravity. Black holes become not only physical mysteries, but philosophical ones. They force us to ask whether time itself can die. And yet black holes are not faraway monsters alone. Their lessons ripple outward, reminding us that every force, every movement, every bit of gravity we feel is already bending our lives. The extreme simply makes visible what has always been true. How astronauts age slower in space. When an astronaut leaves Earth, we imagine they are only stepping away from our planet's surface. But in truth, they are also stepping away from our timeline. Each orbit around Earth bends their seconds differently. Because they're moving so fast, relativity makes their clocks run slightly slower. The effect is tiny, measured in microseconds. But it is real. An astronaut who spends a year in orbit returns ever so slightly younger than if they had stayed on Earth. It sounds like a science fiction story, but it has been confirmed by comparing atomic clocks carried aboard the International Space Station with those kept safely on the ground. The astronauts' time lags behind. They don't feel it. Their heartbeats, their thoughts, their laughter all seem normal, but when measured with precision, the universe quietly admits that their lives unfolded a fraction slower. Think of the poetry hidden here. A year in space is not the same as a year on Earth. When astronauts return, they carry more than memories of floating in silence. They bring back a version of time that does not match ours. Their seconds stretched, leaving them as living proof that relativity is not just theory, but life itself. This is not a trick of imagination. It is the natural consequence of speed and gravity conspiring against the steady tick of our clocks. For the astronauts, it changes nothing day to day. For the scientists, it changes everything, because if time can bend even by microseconds in orbit, what might happen when we venture farther, faster, into the deep? And here lies the whisper of possibility. If astronauts age slower in space, could space travel become a way to glimpse the future? Could voyagers one day return not only from distant worlds, but from tomorrow itself? The quiet secret behind space, travel and longevity. There is a quiet secret hidden in every rocket launch. The moment the engines roar and the spacecraft rises, the people inside are not just leaving Earth, they are stepping into a different rhythm of time. Motion slows their seconds. Gravity's weaker pull in orbit lets their clocks tick faster. These two forces tug in opposite directions, and yet together they sculpt the strange truth. Space travelers are not perfectly synchronized with those they leave behind. This secret has already been measured. Astronaut Scott Kelly, who spent nearly a year aboard the ISS, aged just a little less than his twin brother Mark, who remained on Earth. The difference was small but real. It became a modern version of the twin paradox, lived out not in thought experiments but in flesh and blood. The universe's law of relativity had touched a human life directly. When you think of longevity, you may picture diets, exercise, or medicine. Yet physics quietly reminds us that speed and gravity also play a role. By moving differently, you live differently. By orbiting Earth, astronauts are practicing a subtle kind of time travel. Not to the past, but to the future, by aging just a touch slower than us. The beauty of this truth lies not in its practicality. The differences are far too small to extend life in meaningful ways, but in its philosophy. It shows us that time is not fixed, that every journey we take, every path we walk, is also a shift in our personal river of seconds. Even here on Earth, running up a hill or resting in the valley, we are all living in slightly different times. The quiet secret behind space travel is that it's not only about where you go, but when you come back. And that thought lingers, leaving us to wonder whether future generations will learn to stretch their lives by bending the seconds themselves. A year on the ISS is not the same as a year on Earth. Close your eyes and imagine drifting inside the International Space Station. Outside the window, Earth glows in silence. Inside, astronauts work, eat, sleep, laugh. To them, a year feels like a year. Yet when they return, their clocks don't quite match those on the ground. A year in orbit is not the same as a year on Earth. The difference may be measured in microseconds, but it's undeniable. Their orbiting speed slows their time. Meanwhile, their altitude higher than the surface lets gravity loosen its grip. The two effects push and pull, but the balance still leaves the astronauts living a slightly different version of reality. They come home having lived less time than their family and friends below. This truth is humbling. We speak of time as if it were universal, but the ISS proves otherwise. Two people, separated by orbit and ground, live through different numbers of seconds while still sharing the same calendar. It forces us to ask, what does a year even mean? Is it simply the motion of Earth around the Sun? Or is it the unique rhythm of each observer's clock? The ISS is not only a laboratory for science, it is a laboratory for time. Every orbit reminds us that we are not masters of it, only passengers. The astronauts who live above us become silent proof that the seconds we trust so deeply are already slipping into many versions. A year on the ISS is not the same as a year on Earth. And this truth will echo louder as humanity begins to travel farther, to Mars, to the outer planets, perhaps one day to the stars themselves. Cosmic rays as witnesses of time's stretch. Far above Earth, invisible rain falls from space. These are cosmic rays, high-energy particles born in violent events across the universe. They streak toward us, colliding with our atmosphere at near-light speeds. According to their own internal clocks, many of them shouldn't survive the journey. Their lifespans are too short. And yet, they reach us. Why? Because motion has stretched their time. This is one of the universe's great confirmations of relativity. Moons, unstable particles born from cosmic rays, decay quickly. If time were absolute, they would vanish before reaching the ground. But because they move so fast, their internal clocks slow. To them, their lives still end quickly. To us, they live long enough to touch the Earth. They are witnesses of time's stretch, carrying Einstein's truth in every fall. It is humbling that something so small, so fleeting, can reveal so much. Moons don't argue, don't theorize. They simply live and die, proving that time is not equal. Their very existence on Earth is a quiet announcement. Speed bends reality. The faster you move, the more time waits for you. Scientists have studied moons for decades. watching them rain down from the sky. Each detection is like a cosmic reminder that the universe does not play by human rules. Particles born in the violence of stars and galaxies are already showing us what happens when you dare to challenge the speed of light. Cosmic rays are not only messengers of distant events, they are also proof that the laws of time bend everywhere, all the time. And if particles can carry these secrets, then what about the smallest building blocks of our own bodies? The strange life of muons in Earth's atmosphere. Imagine a muon, a tiny particle, invisible to the eye, born in a flash of energy high above the Earth. According to physics, it should live for just a few millionths of a second before fading away. At the speed it's moving, that's not enough time to reach the surface, and yet countless muons do. How? Their strange lives are stretched by time dilation. To the muon, nothing feels unusual. Its clock ticks normally. Its brief life passes as expected. But from our perspective, its lifetime has expanded. Seconds that should have vanished have stretched, long enough for it to complete a journey it shouldn't survive. The muon becomes a tiny, unknowing time traveler. Scientists measure these particles with detectors on mountaintops and in laboratories underground. Every count, every flash of data confirms the same truth. Relativity is real, alive, and written into the behavior of the universe itself. Muons have become proof, falling quietly around us every day, that the flow of time bends with motion. What's remarkable is that the muon doesn't try to prove anything. It simply is. It lives, it dies, and in doing so, it reveals secrets that humans struggled for centuries to imagine. The strange life of muons is not a story of theory, but of fact, falling from the sky like whispers of truth. Why particles outlive their own clocks? Imagine holding a stopwatch for a particle called a muon. Physics tells us it should vanish in a fraction of a blink, its life too short to matter. Yet when these muons rush toward Earth at nearly the speed of light, they live long enough to be measured. They outlive their own clocks. The question is not whether they cheat death, but how speed itself stretches their brief existence. Inside their own reality, nothing is strange. The muon still lives its tiny, fleeting life, but from our perspective, its seconds stretch. This is the heart of relativity. Time for the muon is not the same as time for us. By moving so quickly, its internal clock slows relative to ours, allowing it to survive journeys it shouldn't. In this way, particles become tiny messengers of truth, carrying Einstein's theory on their backs. This strange survival is measured in laboratories all over the world. Detectors hum quietly, watching as muons rain from the sky. Each one whispers the same secret. Time bends under speed. It's not a trick. It's not an illusion. It's the universe, showing us what it really does when pushed to extremes. Think of the poetry hidden here. A creature meant to live, a blink, somehow stretches into a breath. A tiny life gains length, not through choice, but through motion. And in its survival, it proves that time is never universal, never fair, always relative. These particles, too small to see, carry lessons large enough to challenge our deepest certainties. When you hear that particles outlive their own clocks, it forces you to wonder, do we too live inside clocks that are stretched or shortened depending on where and how we move? And if so, whose measure of time is the truest? Speed becomes a tool to cheat time. Imagine stepping into a spaceship capable of traveling near the speed of light. Inside, your heart beats, your meals are eaten, your laughter sounds normal. Yet when you return, those you left behind are older. Years may have passed for them, while for you only months. Speed itself has become a way to cheat time. This is the strange gift of relativity. The faster you move, the more time bends. In a sense, motion becomes a key to the future. You can't stop aging, but you can slow it relative to others. The effect is not science fiction, and it's been confirmed again and again with particles, with satellites, and with astronauts. Time is pliable, and speed is the hand that shapes it. For humanity, this truth is both thrilling and humbling. It means that future space travelers may return to Earth and find entire generations have come and gone. To them, it may feel like only a few years. To Earth, it may be a lifetime. Speed becomes not just a tool for travel, but a divider of human experience. The idea unsettles us because it touches our deepest fears of separation. If motion can change our very lifespans relative to others, then journeys to the stars are not only about distance, they are about time itself. Leaving Earth might mean leaving its rhythm forever, and yet speed as a tool to cheat time also awakens wonder. It makes us ask, what does it mean to live? Is it measured by seconds on a clock, or by the moments we actually experience? The answer may be as flexible as time itself. Can we really travel to the future? The question lingers in every curious mind. If motion bends time, does that mean we can travel to the future? The answer, quietly but firmly, is yes. Not in the way of science fiction movies with flashing machines, but in the sober language of physics. Each time astronauts orbit Earth, they return a fraction of a second younger than they should be. Each time particles fly near light speed, they outlast their expected lives. The future is already being touched. Time travel to the future is not a doorway you step through. It's a consequence of speed and gravity. Move faster, live slower, hover near strong gravity, and your seconds stretch. When you return, the rest of the universe has aged more than you. You have traveled forward, not by jumping, but by bending your personal clock against the universe's. It's a humbling truth. The future is not something we wait for passively. In theory, it can be reached more quickly by daring to move differently. The faster, the farther, the more extreme the journey, the deeper into the future you go, but the cost is real. The world you left behind may be unrecognizable when you return. This kind of time travel doesn't let you see the past, doesn't let you undo mistakes or relive joy. It is one way, like an arrow pointing forward. Yet even this arrow is astonishing, for it shows us that time is not fixed, but negotiable. Humanity's dream of stepping into tomorrow is not fantasy. It is science waiting for courage. So when we ask, can we really travel to the future? The universe answers softly, you already do every time you move, every time you rise against gravity, every time you dare to test the limits of speed. The science that already proves we do. Skeptics may shake their heads at the thought of time travel, but the truth is, we already have proof. It lies not in distant galaxies or science fiction, but in experiments done here on Earth. Atomic clocks carried on planes have disagreed with those on the ground. Satellites circling Earth demand corrections because their time runs differently. Particles racing through the atmosphere outlive their expected lifetimes. All of this is not theory. It is science already written in numbers. Think about how ordinary it has become. Every time you use GPS, you are relying on time travel being real. Without relativity's corrections, your phone would place you miles away. Every direction you follow is a quiet acceptance that time is not absolute. The technology works only because the bending of time has been measured and accounted for. We live inside proof every single day. This truth feels almost invisible, hidden in plain sight. We look for miracles in distant science, yet the miracle is already beneath our fingertips. Relativity is not a story, it is a working fact. The universe bends time, and our devices, our planes, our satellites, all reveal it in silence. The poetry of it all is that humans, without meaning to, are already time travelers. Not in leaps and dramatic journeys, but in tiny stretches and compressions. Each orbit in space, each movement near speed is a step forward relative to those left behind. We don't have to ask if it's possible. We already live inside the answer. The science that proves we already travel in time also forces us to wonder. If these small experiments are true, what might happen when humanity builds ships to carry us far beyond Earth? Will time travel stop being a quiet fact and become a lived reality? The past is still here, but out of reach. Here lies a haunting thought. If the future can be reached through motion, what about the past? Physics tells us the past is still woven into the fabric of the universe. Every event, every second still exists as part of space-time. The problem is not that the past is gone, it's that it's unreachable. Like a book sealed shut, the pages remain, but we cannot turn back to read them. Einstein's theory paints time as a dimension woven together with space. Just as every location exists, every moment exists too. The past doesn't vanish. It waits silently, recorded in the structure of the universe. But our arrow of time points forward, pulled by entropy, the slow drift toward disorder. This arrow keeps us from walking backward, no matter how much we ache to. Think of it like light from distant stars. We see galaxies as they were millions of years ago, their past still shining toward us. In a sense, the past does reach us, albeit always as a shadow, a memory, a faint echo carried on waves of light. Never as a place we can step back into. The doors behind us close as we walk forward. This truth carries both sadness and beauty. Sadness because we can never relive what is gone. Beauty because nothing is ever truly lost. It's written into the cosmos forever. Your first breath, your first word, every moment you've lived still exists, etched into the universe's fabric like ripples in a pond. Why time feels like a river, yet isn't. When we speak about time, we often describe it like a river, flowing endlessly forward, carrying us along whether we wish it or not. It feels natural to think this way. We wake, we work, we sleep. The days spill into weeks, the weeks into years. But in physics, this image of a steady one-directional river begins to dissolve. Time is not a smooth flow. It is something stranger, bending and stretching, different for each observer. What feels like a river to us is really a perception, or a way the human brain makes sense of change. The ticking of clocks, the rising of the sun, the beat of our hearts. These rhythms give us the illusion of a current, but the universe itself does not promise such simplicity. Two observers moving differently may disagree on how much time has passed. The river is not one stream, it is many, weaving through reality like threads in a tapestry. Think of how unsettling this is. We walk through life believing we share the same now, that our seconds are synchronized with everyone else's. But the deeper we look, the more the river fragments. What is now for me may not be now for you, if we stand in different conditions of motion or gravity. Suddenly the river image crumbles, and yet we cling to it. We need the river because it comforts us. It gives shape to our stories, a sense of beginning and end. Without it, life would feel scattered, disconnected. Perhaps that's why our minds choose to see time this way, as a flow we can float upon, even if the deeper truth refuses to be so simple. Time feels like a river, yet it isn't. It is a network of currents, shifting with every perspective, every place, every speed. And once you glimpse that truth, the question of now becomes even more mysterious. The illusion of now in the universe. Take a quiet moment and ask yourself, what is now? This instant, this second, we believe it to be shared, universal. But relativity reveals that now is not absolute. What feels like this very moment to you may not be the same moment to someone moving differently or standing in stronger gravity. The universe does not grant us one single now. This realization feels almost unbearable at first. Our lives are built on the comfort that when I speak to you, we are sharing the same moment. But in truth, each of us carries our own slice of time, tilted by motion, bent by gravity. The illusion of now is a gift of perception, not a law of physics. Imagine two astronauts drifting far apart, one near Earth, the other racing through deep space. Each believes they live in the present. Yet their present moments may not align. What one calls now could be the other's then. The idea unsettles us because it cracks the sense of togetherness we take for granted. It tells us that reality itself is layered, like overlapping sheets of glass, never perfectly aligned. And yet there is beauty in this illusion. If now is not universal, then every observer holds a unique slice of reality, a private window into the cosmos. Our shared experiences are not diminished by this. They are enriched. The universe allows billions of different nows to exist simultaneously, like stars scattered across a sky. The illusion of now is perhaps the most human of all, for even if physics tells us it doesn't exist universally, we live it, we feel it, we believe in it. And maybe that belief is what makes life bearable. Every observer lives in a different slice of reality. Close your eyes and imagine the universe as a giant loaf of bread. Each slice is a different moment in time, a different reality. Where you stand, how fast you move, and what gravity presses upon you decides which slice you are experiencing. Every observer lives in a different slice of reality, shaped not by choice, but by physics itself. This is what relativity tells us. There is no single, objective view of the universe. What you measure may not match what I measure, and both of us are correct. It is a truth that humbles human certainty. Our reality is personal, shaped by the conditions of our journey. The cosmos does not grant a single master clock. It grants countless local truths. Imagine astronauts orbiting Earth while we remain on the ground. Their seconds stretch differently than ours. Their slice of reality is shifted ever so slightly. To them, life feels ordinary, yet from our perspective, they are aging at a different rate. They are not living the same universe we are. They are living their own slice. This perspective forces us to rethink togetherness. We are never fully in the same place, the same time, the same reality. And yet somehow we still share meaning, still connect. Perhaps that is the miracle, that within all these slices, love, memory, and language find a way to overlap, like bridges across invisible gaps. Every observer lives in a different slice of reality. And once you accept this, you begin to see that the universe is not a single story, but a library of countless overlapping pages, each one true, each one alive. When astronauts call Earth, which now is real? Picture an astronaut calling home from orbit. Their voice travels through radio waves across the silence of space back to Earth. On their side, it feels like the present. On Earth, it feels like the present too, but whose now is real? Relativity tells us that both are, and neither is. Their timelines are not perfectly aligned. The astronaut's clock, bent by speed and altitude, ticks differently than the clock ticking in the control center on Earth. To the astronaut, seconds flow normally. To the earthbound listener, they also feel normal, but measured against one another, they diverge. When they speak, their words bridge two slightly different versions of reality. This truth is unsettling, but also strangely comforting. It means that communication itself is a miracle. Two beings living in different slices of time can still hear each other, still share laughter, still say, "I miss you." The physics may argue that now is relative, but the human heart finds a way to create a shared present anyway. Think of how small delays in phone calls already remind us of this. A pause, a lag, a beat of silence before a reply. Even here on Earth, distance bends our sense of now. In space, that bending becomes both more dramatic and more profound. It reveals that the human experience of time is more about connection than clocks. So when astronauts call Earth, which now is real, the answer is simple: both. And perhaps that is the deepest truth of all, that reality is flexible enough to hold two truths, and yet love is steady enough to bridge them. Time zones in the cosmos are not human-made. On Earth, we divide time into zones. Noon in New York is night in Tokyo. These zones are human inventions, carved to match the turning of the planet. But in the cosmos, time zones are not man-made. They are written by relativity itself, carved by motion and gravity into the fabric of reality. Every planet, every orbit, every speed carries its own clock. A day on Mars is not a day on Earth. A year near Jupiter's moons unfolds differently than a year on the ISS. These differences are not arbitrary, and they are demanded by physics. Time zones in the cosmos are not agreed upon by governments, but by the universe itself. This truth becomes crucial as humanity prepares to expand into space. Colonists on Mars will live under one rhythm, astronauts orbiting Venus under another. Communication between them will require more than language. It will require understanding that each world, each orbit, is its own zone of time. A cosmic map is not just of distances, but of rhythms. And yet this cosmic truth already touches us on Earth. Satellites orbit in one rhythm, planes fly in another, mountain tops in yet another. Without even realizing it, we already live in multiple zones of time, not only by daylight, but by relativity. Time zones in the cosmos are not human-made. They are whispers of the universe's deeper design, reminding us that we are passengers, not masters, of the clocks that guide our lives. The expanding universe pulls time apart. Imagine looking at the night sky and realizing that everything you see, every star, every galaxy, is drifting away. The universe itself is expanding, stretching space like a balloon, and as space stretches, so does time. The expansion of the universe is not just about distance, it pulls on the very rhythm of moments, making time itself feel different depending on where you stand. Think of galaxies at the edge of our view. They are not only far, but they are racing away faster and faster as the universe expands. For them, time unfolds differently. Their clocks are not our clocks. Their seconds do not align with ours. In a way, the expansion pulls reality apart, leaving no single universal rhythm to guide the cosmos. This is difficult for us to grasp because we crave unity. We want to believe in one shared moment, one shared ticking clock. But the truth is that each galaxy carries its own version of time, stretched by the expansion itself. Space and time are inseparable, and when one stretches, the other follows. The poetry of this is haunting. Time, which we thought of as eternal and steady, is being pulled, molded, shaped by the silent growth of the cosmos. Each second here on Earth is not the same as a second billions of light years away. Expansion is dividing the universe into countless rhythms. The expanding universe pulls time apart, and as we watch the galaxies drift, we are not only looking into space, we are looking into many different versions of reality's clock. Light from distant stars is already ancient. Look up at the stars tonight and remember, you are not seeing them as they are, you are seeing them as they were. The light from those stars has been traveling for years, centuries, even millennia before it reaches your eyes. By the time it arrives, the star may have changed or even died. The light is ancient, a message from the past, frozen in its journey. This truth means the night sky is not a present moment. It is a museum of time, a gallery of old events still shining toward us. When you gaze at Orion, you are looking back hundreds of years. When you see the Andromeda Galaxy, you are looking back millions. The universe hides its history in plain sight, written in starlight. There is a quiet wonder in this. Every glance upward is an act of time travel. You are not only witnessing beauty, you are witnessing memory. The light carries stories of explosions, of births, of deaths, of galaxies swirling long before human eyes ever opened. You are not standing in the present. You are standing in a mixture of pasts. Think of how this changes perspective. The stars above you are not twinkling in real time. They are ghosts, delayed by distance. Some of them may not even exist anymore, and yet their light continues to tell their story long after their silence has come. Light from distant stars is already ancient. And in that truth, we realize the universe does not just show us space, it shows us time itself, stretched across the heavens. Looking at the sky is looking into the past. Each time you tilt your head upward, you are not simply looking at stars. You are looking back in time. The further away the light source, the older the story it carries. Telescopes are not just instruments of sight. They are instruments of memory, collecting echoes from billions of years ago. To look at the sky is to peer into the universe's scrapbook. Astronomers use this truth like detectives. By studying galaxies billions of light years away, they are actually studying the universe when it was young. Each faint glow is a time capsule carrying the conditions of a long-lost age. In this way, the sky becomes a living record of the past, stretching back to the very birth of everything we know. This is what makes cosmology so mysterious. You cannot study the universe as it is. You can only study it as it was. Even the sun you see each day is 8 minutes old, the time it takes light to travel from its fiery surface to your waiting eyes. Everything is delayed, everything is ancient, nothing is truly now. The poetry here is irresistible. Looking at the sky means sharing space with ghosts, with echoes, with long-lost moments that still shine. The stars are not only beautiful, and they are storytellers whispering across time. And by listening, we are forever bound to a past that refuses to disappear. So yes, looking at the sky is looking into the past. The question then arises, how far back can we see? And what does the oldest light of all reveal about time itself? Why the early universe still echoes in the present. Billions of years ago, when the universe was young and hot, it left behind a faint whisper of light. That whisper still surrounds us today. It is called the cosmic microwave background, a thin glow that fills the entire sky. It is not visible to the eye, but sensitive instruments can detect it. And in that faint echo lies the memory of the universe's childhood. This radiation is the afterglow of the Big Bang, stretched by expansion into microwave frequencies. It is the oldest light we can see, frozen in time, carrying information about a universe only 380,000 years old. In its patterns and ripples, scientists read the story of how galaxies would one day form, how matter gathered, how time itself was born into order. What makes this so haunting is that the early universe is still here, still speaking, still woven into the fabric of our present. Every moment you live is carried inside that same universe, expanding and cooling since those first seconds. The echo never left. It simply became faint, quiet, waiting for us to learn how to listen. This background light reminds us that the past is not gone, it is preserved, not in books or memories, but in the very radiation filling the cosmos. To see it is to look at the universe's first photograph, a baby picture printed across all of space. The early universe still echoes in the present, and in that echo lies the greatest reminder of all, that time is not separate from us. It is the fabric we are stitched into, and it has been whispering its story since the beginning. Cosmic microwave background as a frozen clock. Think of the cosmic microwave background not just as light, but as a clock. Its ripples, its patterns, its faint fluctuations are the frozen ticks of the universe's earliest seconds. Scientists study them like archaeologists, uncovering the record of time itself. This background radiation is not only evidence of the past, it is the universe's first clock, still ticking silently in the background. Every tiny variation in that faint glow tells us something about the state of the universe billions of years ago, how matter was spread, how energy danced, how the seeds of galaxies were planted. By measuring these fluctuations, we can trace the age of the universe, its expansion rate, its destiny. The clock is silent, but it speaks in numbers that stretch across eternity. What is astonishing is how universal this clock is. No matter where you are in the cosmos, Earth, Mars, or some distant galaxy, the background glow is there, surrounding you. It is the one timepiece every observer shares. In a universe where time is relative, the cosmic microwave background becomes the closest thing to a universal calendar. But even this frozen clock is not immune to the expansion of the cosmos. As the universe stretches, so does the background light, becoming fainter, cooler, harder to detect. The ticks are still there, but drifting away from us like a watch buried deeper and deeper in sand. The cosmic microwave background is a frozen clock, reminding us that time itself has a history, a beginning, and a record written across the stars. And as we follow this clock, we drift into questions about galaxies racing away, expansion speeding up, and what that means for the future of time. Galaxies that drift away faster than we can measure. Imagine staring into the deep night sky through a telescope. You see galaxies, faint smudges of light, each holding billions of stars. But here is the unsettling truth. Many of those galaxies are racing away from us faster than we can ever catch. The expansion of the universe is not slowing down, I'd say it is speeding up. Some galaxies are drifting so fast that their light will never reach us again. This acceleration means we are losing sight of parts of the universe. Over time, more galaxies will slip beyond the horizon of visibility, carried away by the stretching of space. What once was part of our cosmic neighborhood will vanish, not because it ceased to exist, but because the expansion pulled it away faster than light itself can bridge. Think about how haunting this is. The universe is not a static picture, it is a moving stage, and the actors are slowly exiting beyond the curtain, never to be seen again. Each night sky you admire is already temporary. Galaxies visible today may be invisible tomorrow, lost to the accelerating tide of expansion. Scientists call this the cosmic horizon, a boundary beyond which we can never look. It is not a wall, not a barrier, but a consequence of expansion itself. Galaxies crossing that line become unreachable, as if the universe were slowly dimming its own lights. Galaxies drift away faster than we can measure, and in their departure lies the reminder that our universe is not eternal in sight, but fleeting in vision, carrying time away with distance. The universe expands, but does time expand too? When we think of the universe expanding, we imagine galaxies moving apart, space stretching, distances growing. But the deeper question is this: does time expand as well? If space and time are woven together, then as one stretches, surely the other must respond. Could it be that the very flow of seconds is changing as the universe grows? This is not an easy question. Scientists debate whether time itself is slowing or speeding on a universal scale. But we do know that the expansion alters how we perceive distant events. Light from galaxies is stretched into redder, longer wavelengths, not just because of distance, but because time itself between the flashes of light has been stretched. In that sense, yes, time expands. Think of it this way. Imagine a drumbeat echoing through space. If the universe expands, the beats grow further apart, delayed, stretched. To us, it feels as though time itself in those distant galaxies is running slower, but for those living inside them, their clocks tick normally. It is our perspective, our place in the expanding fabric, that makes the rhythm feel longer. This dual truth is what makes cosmology both wondrous and strange. Each observer experiences their own flow of seconds, yet the expansion ensures those flows never align perfectly. The universe is not only growing in size, it is growing in diversity of time itself. The universe expands, but does time expand too? The answer seems to be yes and no. Locally, time feels normal. But cosmically, the beats between moments are stretching further and further apart, leaving us with a sky full of echoes that drift slower and slower into silence. Dark energy and the speeding up of tomorrow. In the late 1990s, astronomers made a discovery so shocking that it reshaped our understanding of the universe. By studying distant exploding stars in supernovae, they realized the universe was not just expanding, it was accelerating. Something unseen, something mysterious, was pushing galaxies apart faster and faster. They called it dark energy. Dark energy makes up about 70% of the universe, yet we cannot see it, touch it, or measure it directly. We only know it exists because of its effect. It speeds up expansion, and in doing so it bends time itself. The faster galaxies race away, the more their light stretches, the more their moments drift apart from ours. Dark energy doesn't just shape space, it shapes the rhythm of tomorrow. This force is invisible, but its consequences are enormous. In billions of years, galaxies beyond our local cluster will be forever lost to view. The night sky will grow emptier, quieter, lonelier. Humanity, or whoever is alive then, will look up and see fewer stars, unaware of the vast universe that once existed beyond. Dark energy feels almost like a thief, stealing the future's view of the cosmos. And yet it is also a creator, weaving the fate of time itself. Without it, the universe might have slowed, collapsed, or grown differently. With it, the arrow of expansion continues forever, stretching seconds and distances alike. Dark energy and the speeding up of tomorrow remind us that the universe is not done writing its story. The ending has not yet been revealed, and perhaps the greatest mystery is whether time itself will one day run out of pages. Can the end of time be written in cosmic equations? Physicists often ask daring questions. One of the boldest is this: could time itself end? If the universe is governed by equations, then perhaps those equations carry within them a final moment, a point where the ticking of clocks ceases altogether. The thought feels unsettling, like standing at the edge of a cliff and peering into fog. Some theories suggest a big rip, where expansion grows so extreme that galaxies, stars, planets, even atoms, are torn apart. In such a universe, not only would matter vanish, time itself might no longer have meaning. Others imagine a heat death, where everything spreads so thin that no energy, no change, no motion remains. And without change, can there be time? What makes these ideas haunting is not just their scientific weight, but their philosophical echo. Time feels eternal to us because we live within it. But if it is a property of the universe tied to its structure, then it can begin and it can end. And our personal moments are but brief sparks in that larger story. Yet even as scientists write equations for these possible endings, there is humility. No one truly knows. Perhaps time is larger than the universe we see. Perhaps it continues beyond what we can imagine. Perhaps the end is simply the edge of our current understanding, not the edge of reality itself. Can the end of time be written in equations? The universe remains silent, and in that silence lies both fear and wonder. Time at the edge of the observable universe. When we peer into the deepest parts of the sky with telescopes like Hubble or James Webb, we are not looking at galaxies as they are today. We are looking at them billions of years ago, frozen in ancient light. This is the edge of the observable universe, a horizon set not by distance, but by time itself. At that edge, we see galaxies as they were just after the Big Bang, faint smudges of youth in a cosmos that was still learning how to form stars. Beyond that edge, light has not yet had time to reach us. Not because the galaxies don't exist, but because time itself has not been enough for their messages to arrive. It is humbling to realize that the universe we see is not the universe that exists. We live inside a bubble of visibility shaped by the finite age of light and time. Beyond it lies a reality we may never touch, perhaps infinite, perhaps finite, always hidden by the limit of time's reach. This edge is not a wall. It is a horizon always moving, always expanding as the universe grows older. Each year, more of the cosmos becomes visible. Yet each year, expansion also carries parts of it away, beyond reach forever. We are caught between revelation and loss. Time at the edge of the observable universe reminds us that knowledge itself has limits. We can see far, but never all. We can measure much, but never everything. And in that limit lies both frustration and awe, for it means the universe will always remain a mystery just beyond our grasp.